Hello viewers, you are welcome to this information session on the upcoming bootcamp on MATLAB for engineers brought to you by the GAD Academy. My name is Martin and I'm going to be your moderator for this uh, session as well as your instructor for the main bootcamp. Now this um, session is supposed to inspire you and give you a bit of an introduction to what MATLAB is, why engineers need to use MATLAB, what are some of the things we can obtain, some of the skills we hope to gain from understanding of MATLAB, and really all the benefits and the great things that tools like MATLAB does for humanity. Now, if we start from first principle, humanity has needs. Right? The earth as we see it is raw in its nature, and there are problems all over. So one thing we see all around us is the presence of problems in different forms. Right? We human beings need water. We need access to safe water and sanitation. We need energy for transport, for so many things, to power systems that we rely on. Um, there are climate issues, the pollution, and the buildup of pollutants in our atmosphere is an ongoing problem that engineers are looking to solve. Urban infrastructure, road networks, proper housing, and all of these current challenges that we face. So there's always problems in our daily lives. So there are always problems around us, and engineers are always looking to solve one problem or the other. Now, what we usually find in nature is that uh, in as much as there are many problems, there are also resources around us, right? There are resources available, and the job of the engineer is to create things that have not been seen before. So what happens is nature has resources. However, human needs vary a bit. So we have sunlight, for instance, which is an abundant source of energy from the sun. However, the most useful form of energy for humans is electricity. If you take petroleum, for instance, this is stored, it's valuable energy, but it's stored deep beneath the earth. We need it on the surface of the earth to power vehicles, planes, and systems that use that fuel. If we talk of water, one of the most abundant resources on the surface of the earth, it's on the surface in large volumes. However, it barely comes in the form that we need. When you talk of drinking water, the ocean as it is not safe for drinking. And there's a gap between the raw material, the raw resource as it is, and the form in which we need it. Water, for instance, flows downhill as a result of gravity. However, there are times where we need water to flow in the opposite direction. You may live on top of a story building and need water that is sourced from the surface to reach you. So what engineering does is to bridge the gap between those natural resources and our human needs. And we do that by developing systems or technologies that convert these raw materials or their raw forms into the versions that suit human needs. So if you look at the case of energy, sunlight, for instance, can be harvested using solar panels and then converted, uh, transmitted over grid lines to reach homes. It can be stored in batteries for subsequent use. Petroleum is extracted through drilling technologies, refined into several products, and these products are transported to or distributed to humans. Water is dammed and treated in plants or water treatment plants, and then it's also conveyed and delivered to humans for use. So we see all around us that uh, engineering solutions are part of our everyday lives. So these are some of the solutions that come as a result of engineers create to bridge these gaps. We have, for instance, the water plants, the solar panels, the manufacturing plants that produce our everyday goods that we use. Now, there are important questions that engineers ask whenever we have to design systems to solve problems. We want to know whether this thing will work. So if you face a problem and then you decide to come up with a solution, uh, you want to know whether the thing will work in the first place. And some of that might be if you were creating machine parts, will they break? Under which conditions will they survive? And will they be able to work under the conditions or the intended use? Right? If you had a reactor, maybe you wanted to produce soap and you reacted caustic with fats, you want to know whether it will react at all. You want to know whether at the end of the day you are going to get that soap if you put this and this together. Um, your distribution lines, you want to know whether they're able to send the required power to the destinations you intend, and so on. So there are a lot of questions that need to be answered whenever engineers come up with solutions or attempt to solve problems. However, there is a challenge in answering these questions. So the problem here is that we could build these things first, maybe whatever the solution is, you could build them and then try to impose conditions on them. But you realize that, first of all, that can be very expensive if you have to build systems over and over and over again to test them under different conditions, to increase your confidence on to uh, give you that confidence that the system is going to work. In other cases, some systems are just unsafe to study in that manner. You cannot build the full system and then explore it directly as such. And some of them you cannot even simulate in any real way, right? So if you wanted to construct a building and you wanted to know under what wind stress conditions your building can withstand, right? Or if you want to know what weather conditions are going to adversely affect your building, it's going to be difficult to impose specific wind velocities on your building to study the behavior of the building under those conditions. So what happens is that there is a gap between these questions and our ability to answer them in reality. So that brings us to the need for models. We need tools that can mimic these systems that we want to create without the need to interact with the real system. However, the models are supposed to be accurate representations or fairly competent representations of the real system that we can study, right? We can study safely, effectively, quickly, and then obtain reliable solutions for subsequent design. So that is what the important needs, or why modeling is an important part of um, engineering process, and as part of engineering culture. Modeling and simulation, you cannot do without them in engineering now. So if we talk about models, right? One of the most fundamental four kinds of models you can have is mathematical models, right? And almost most engineering systems are described by some form of mathematics. It could be a system of linear equations, partial differential equations, um, and several other systems that are used, mathematical systems or models that are used to describe engineering systems. Now, these mathematical models, some of them are inherently complex, and even when they seem to be simple, depending on the nature of the system you are dealing with, you could move from a very simple problem to problems with serious complexity very quickly. And so if you look at system of linear equations, when you have two, three, maybe up to three linear equations, there are analytical methods that can solve that, and we may have studied some of those in class. However, once you are dealing with real systems, maybe you have a whole plant and you're performing a material balances on that plant to determine what comes in, what goes out, and so on. You quickly run into large sets. You can have 200 or more equations with several variables that need to be solved. And it's near nigh impossible to do this in any by any manual means. So the problem there becomes engineering problems by nature. The kind of problems that um, engineers deal with are complicated. So we first try to predict these things using mathematical models. However, when it comes to obtaining solutions or probing these mathematical models for uh, insights, we find out quickly that their complexities pose a challenge. So what then do we have, or what tools do we have available to deal with this? And that is where simulation tools come in. And because engineering problems don't come with simple answers, and models can easily get or become complicated, we need powerful tools, and that is where we have computers. Now, computers allow us to perform complex computations within a short or reasonable period of time at a low cost. So those complex differential equations and system of linear equations that will take forever for a person to solve by hand can be quickly solved within a matter of minutes by a computer. So MATLAB is one of the tools for engineering solutions that allows engineers to model problems mathematically and uh, probe these mathematical models for solutions and insights into systems that are of interest for the engineer. So if we talk of the kind of challenges that we have designing grid systems to supply power to a whole city or countries, if we talk of having to manufacture goods to supply several continents and hundreds or billions of people, we quickly realize that we are dealing with large scale problems. No matter how inherently simple or complex the problem is, once you scale to solve a problem for large masses, inherently the problem becomes complicated. So we have MATLAB for some of these. It can perform computations, dealing with system of equations, solving differential equations, visualizing data, and basically a lot of the tools engineers use to analyze systems can be handled using MATLAB. It's also applied across a lot of engineering disciplines. Mechanical engineers can use MATLAB to perform stress simulations to tell whether materials will fail under certain conditions of temperature, pressure, um, or duress. Electrical engineers also use uh, MATLAB and Simulink or some of the other components of MATLAB to analyze circuits, perform signal analysis, and other electrical related or electronics related simulations. Civil engineers likewise can also use um, for structure analysis, and chemical engineers use this for equipment design, or process engineers for equipment design, modeling the operation of equipment, and control systems. Aerospace engineers can also use this for aerodynamics, and there's MATLAB has capabilities of merging with uh, traditional computational fluid dynamics softwares for more expanded modeling. Right, so it has a host of functionalities, and it's a very competent and common or popular tool among engineers. So when we look at the reasons why we need MATLAB, it becomes very clear that if you want to, for instance, in the case of modeling reactors, you may want to model concentration and pressure profiles along a reactor. You have to solve equations of several forms. Um, you you have to analyze data, automate work. Sometimes when you create algorithms that perform certain calculations, you do not want to have to do it over and over again. So MATLAB gives you the platform to basically build systems or models that enable you quickly analyze engineering problems and then automate work. And then after automation, you can then probe that model for several scenarios and any different inputs and so on, and without having to build a model again. So it's really the language for engineers. If the full meaning there is mathematics laboratory, that is where the word MATLAB comes from. And if you look at that word, the syntax for MATLAB is actually based on math. So it's very intuitive and one of the easiest programming languages to quickly get used to. Now it's used across the entire engineering space in the oil and gas field, pharmaceutical, aerospace, energy, as we've looked at. Basically, several sectors that provide solutions or engineering solutions for the world. So this course is meant to build your competence in MATLAB by training you, first exposing you to the fundamentals. That is what the first module is supposed to tackle. So we just look at the syntax, understand the basics of the MATLAB programming language, and then general understanding of programming structure, right, which is very key to build complex programs later on. Then we look at how to use MATLAB to solve mathematical problems that commonly show up in engineering. We look at linear algebra, finding roots, integration, and then symbolic math. And then we use those tools or our knowledge with which we are equipped at that point to solve more complex engineering problems or apply them to deal with real engineering uh, situations or problems. Now, at this point, it's very clear why um, a person or the benefits a person looks stands to gain from being equipped with this tool. It's industry relevant, and competence in MATLAB is going to put you at an advantage, right, within the industrial space. Uh, Industries are constantly looking for solutions to problems. They're looking to optimize operations and systems. They're looking for innovations. They're looking for um, new solutions to old problems and new problems alike. So having these skills on hand will position an individual to be relevant within their respective industrial space. It's also going to build your problem solving and analytical skills or analytical abilities. Data analysis and visualization is also a very important and common requirement these days. So many systems are moving into dealing with data informed decision making, and consistently it's appearing that a skill an engineer needs, regardless of the field they work in, is the ability to handle and manipulate data. So this is also going to build your understanding or your ability to manipulate data and then draw inferences from data, and it's going to build a strong foundation for you to move on to complicated fields later on that are proving crucial in today's world, including AI, machine learning, and among others. So what does a person need for this course? Um, it's because it's the fundamentals. This is the initial stage or the first module that looks to build on the fundamentals of the programming language. You just need a ready to learn mindset and motivation, right? And hopefully this session aims has done some of that, has built some of that motivation for you. You also need consistency and practice. Programming skills improve the more you apply them. It's an everyday thing, almost a habit, and you need to develop a lot of muscle memory when it comes to programming. You need basic math because that is the one engineering language, and it's also what MATLAB is built on. Then dual programming, making mistakes is a common thing. Whilst you are learning, you learn from them, you learn new ways of doing things, more efficient ways of solving the same problem. And then if you have some prior coding experience, that is helpful. It will smoothen the trajectory for you. However, you do not require it for this course. We are looking to train you from zero to um, real competence. So this is meant to demystify some of the myths around programming or programming for engineering purposes. Uh, Really, some problems, of course, problems can be complicated as we've seen earlier. However, it does not take a genius to know how to program. Everyone can learn how to write programs. And what matters more is an understanding of structure, right? The system you're dealing with. You just need to understand the system you're dealing with, and then writing a few lines of code can help you achieve a lot. So this is just an example of a reactor. Process engineers might encounter this at some point during their studies and in practice. So a reactor is just meant to produce something via chemical reaction. And this allows us to see how much material we are able to produce from a given amount of input. Right? So you realize that you can obtain very impressive solutions uh, with just a few lines of code. So it's not always that hard. Now, I'm your instructor. My name is Martin Emmanuel Palu. I'm a chemical engineer, and I specialize in process systems engineering and the use of modeling and simulation tools to provide engineering solutions for the world's problems. Right, so I'm going to be your moderator throughout the course, and hopefully we'll have an exciting time. So if you are motivated, I believe if you come all this way, you are motivated to learn, and you can simply do that by enrolling via the GAD Academy, which is the sponsor for this program. And you can do that by accessing the Google Forms provided at the bottom of the screen. And then you can register, and then that's all it takes. You are going to be exposed to a world of impressive simulations and impressive solutions and tools. Right. So that brings us to the end of this um, session. If you have any questions, you can put them in the chat. I will try to answer them. So there's a question as whether you can start it as a weak math student. I do not know exactly what you mean by weak math students. However, as much as possible, we try to cover the mathematical basis of whatever we do. So give it a try. Right? There's no harm in trying, and you only get to know if you try. Do not be discouraged early on. And yeah, so someone asked if it's a paid course. Um, no, it's not a paid course for now. The first module, as I understand, is free. So you just have to sign up and then you can start learning MATLAB. We'll try to improve on the audio uh, as time goes on. So there's a question on how MATLAB can be used in pharmaceutical industries. That will depend. I think a pharmaceutical engineer is, or someone in the pharmaceutical industry is much better placed to answer this question. However, off the top of my head, I know pharmaceutical industries still have to deal with the synthesis of drugs, and some of those involve chemical reactions. Even the um, absorption or bioavailability of drugs in the human body also undergoes kinetic processes, right? And these are modeled via kinetic representations or reactions. And that is one of the capabilities of MATLAB, right? So if we talk about pharmacokinetics, uh, that is one way in which MATLAB can be used. I also know I've met pharmacists or chemists who have been interested in using computational fluid dynamics to study the movement of drugs in uh, blood vessels and so on, right, in the body, biomedical engineers as well. So that may be of interest. And I'm sure there are a lot more applications within the pharmaceutical industry that I may not know of, but uh, that's a few of them. I believe programming is necessary for every engineer. Someone is asking if MATLAB is necessary for mineral engineers. Um, I I don't know what specification you have, but for instance, process engineers also deal with metallurgy. And if that is what you're talking about, then yes, that is really one of the domains for MATLAB. You model mineral processing involves several unit operations that need to be designed and appropriately modeled and synthesized to ensure optimal delivery of product. Right, so gold processing plants have a number of processes, comminution processes, where you break down ore into uh, forms with larger surface area so that you can leach the valuables from the ore. You go through several processes, adsorption, and so on, waste treatment, water treatment. Mineral processing involves a lot. And that is a rich space for the application of programming tools like MATLAB. So yeah, you are not out of place at all if you're a mineral processing engineer. Habits, for now, I believe as the course goes on, when there are recommendations for best practices or habits, we would inform you. But right now, I think the one that comes to mind is focusing on structure and understanding of the system rather than trying to memorize code, right? And there's a myriad of solutions or syntax solutions when it comes to dealing with problems. And that really is not of value. There's so much code to be memorized that if you decide to go down the programming route by memorizing code, I believe you struggle, especially when it comes to adapting the things you've learned to other systems. So what's more important is understanding code structure, understanding how the fundamentals of the programming language you're dealing with, and then understanding the systems that you want to model. That is key. Right, so focus on understanding rather than memorizing syntax. When it comes to the projects format, we'll see. If there is the need to develop groups or if it becomes possible, because you guys are um, probably spread out. I do not know the locations or the geographic placing of the viewers and learners. Maybe creating group projects might be a challenge. However, if it proves that that is a possibility, we'll do that as well. But for now, they are going to be individual assignments. So you can keep that in mind. So we spent a lot of time here, and if there are no other questions, uh, I'm going to thank you very much for your time and bring this session to an end. So thank you all for your presence and your time. Um, I'll see you when the course starts officially on Monday.